Hello and welcome to Toddcast number 42. Continuing from last time. So last time we talked about just the alkyne itself. We can deprotonate a terminal alkyne. The pH or the pK is around 26. So if we use a strong enough base, turn it into a nucleophile. We reviewed the fact that it's a 180-degree angle because it's sp hybridized, and just the basics of structure. So I want to start in the actual reactions of the pi bond. And on the positive side, the good news, pretty much every reaction we're going to do is the exact same reaction we did to an alkene. So to an alkene pi bond, very, very similar to what we're going to do to an alkyne pi bond. Few differences. In an alkene, that bond angle is 120. So theoretically, there's more steric hindrance than an alkyne, which has a bond angle of 180. So things that we did, and we got Markovnikov versus anti-Markovnikov addition for an alkene. We can use those same reagents, but we have to modify them to make sure they're perhaps just a little more bulky or a little more efficient at what they're doing. But all in all, it should be very, very similar. And so I want to start with a few simple reactions. And first one is hydrogenation. So let's revisit alkenes for a moment. And if you recall, we added H2 and PT. And if you remember, we had a little bit of PT oxide, just a little oxide in there to help facilitate the binding of the H's to the platinum surface. This time, you'll notice a new reagent, barium sulfate, and explain why that's in there. So let's look at what we get from that. So just like before, we got syn addition with an alkene, we get syn addition with alkyne. But you'll notice this is an alkene. So in theory, we should add 2 more H's. So it should go straight from the alkyne, add 2 to make the alkene, and 2 more to make the alkane. But barium sulfate, the purpose of barium sulfate in there is to poison it. So it serves to stop it at the alkene. So this is one thing a little bit different. So again, we make some modifications, it's similar reactions, but with a slight change. So the presence of barium sulfate. I want to make note, we also have an oxide form of platinum in this reaction as well in the catalyst. Again, just like with the alkene, it's a very small percentage. For the terminal alkyne, same story. We're going to go ahead and add HP2 or H2PT and barium sulfate. Again, it stops. It's syn addition, just like before. And just want to note, if we didn't have that poison, it would keep on going. Okay, the key thing here with this reagent, it works on either internal or terminal. And even though with the terminal one, there's 2 H's, so whether it was trans or cis wouldn't really matter because you're getting the same product either way. Just important to know that in case we have some stereospecific synthesis that's involved in. Want to make note, we could also use calcium carbonate as a poison, and then the percentages of the oxide and a few other reagents in there would change. And so rather than continually try to say what reagent it is, for instance, as you learned, we could use palladium or rhodium as well. For this one, pretty much just platinum with the various poisons, but I'm going to just use the phrase from this point on, Lindlar's catalyst. Kind of a catch-all phrase to describe a poison platinum with H2 combination. So if you just say Lindlar's catalyst, that covers all our bases of what's in there. Without the poison, we just did H2 with platinum. And note that the brackets around the C, parentheses C, means what we're dealing with is platinum on the surface of carbon. And so the way we do this, if we just use platinum, just a chunk of platinum, the reaction only occurs on the surface, so we'd waste all the interior platinum. So one option, one thing we do when we need more surface area is we powder a solid. If we powder platinum, we make it so hard to recover that it's very wasteful, very expensive. So what we choose to do is we take platinum and we put it in its cationic state, put it into electrochemical cells, specifically the cathode where reduction occurs. We send current through it, it plates out of the surface. Well, neat little fact, graphite, because of its extended conjugated network, conducts electricity. So we can make an electrode out of graphite. So we make the cathode out of graphite. We plate some platinum on the surface, put the oxide on there, and we're good to go. So that's what the parentheses C means, is it is plated out onto carbon. Okay, so just a reminder, if we didn't have the poison, it would have the 2 red H's, syn, and then it would add two more H's, the designated in blue, syn as well. So the poison stops at an alkene. That's the whole point. Okay, we might always want syn addition. We may also want anti-addition across one another. And one phrase I want to bring up is when we worry about stereochemistry in the final product. So let's say we start with a stereospecific compound. It's easy to look at what the stereochemistry is going to be in the final product because we know backside attack for SN2, for instance. We know syn addition, anti-addition for alkenes. I'm going to refer to this as kind of like stored or potential chirality. With a geometrical isomer, it isn't chiral in the sense it doesn't rotate plane polarized light, but there still is some chirality or potential chirality in that if it's cis, the two H's, or if they're trans, the two H's, then what we'll end up getting is an easier way of getting an RR compound or RS, SR, SS, whatever the chirality is of the final product. We need to specifically have cis addition and anti-addition. Okay, back to this reaction. If you recall, NaNH2 in ammonia solvent was what we used to deprotonate in terminal. And so this combination of reagents, it works really well for the internal. It can add anti, put two H's on anti. But when we react with the terminal, it ends up that we don't add across. Instead, we deprotonate. So this turns into NaNH2, reacts with itself, and you end up forming a deprotonated alkyne. So same thing we were doing last video where we deprotonated, made a great nucleophile. So the unfortunate thing is this method doesn't work on terminal, only works on internal. And it's not as big a deal as we may think because, again, whether it's going on syn or going on anti, when it's terminal, it really wouldn't matter whether the red H's are cis and this H is trans, or the red H's were trans and this one is cis. It makes no difference. So we really don't need to be able to add trans or cis specifically to a terminal, only the internal. So good enough, we're set. And then the other thing that's interesting is this reagent is both used to deprotonate and add across. And so just curious how the first person came up with this reagent. If it actually, sometimes there's reactions we use that were born out of mistakes. So maybe they added the wrong combination and discovered that you did this trans addition. Whatever the story, it's kind of interesting, but also useful synthetically that we can add syn or trans. So syn addition adds the same side, anti-addition adds opposite side, so we either get cis H's or trans H's. Okay, I've beaten hydrogenation thoroughly into the ground. So next on the agenda, I want to beat hydration into the ground. And if you recall, with the alkenes, we could add either Markovnikov addition or with anti-Markovnikov addition. So let's start with the same thing we did, same reagent we used for an alkene, excuse me. We use BH3, and if you recall, the H would coordinate near the more crowded carbon, and the B with whatever is on it would coordinate near the less crowded carbon. So you'd end up with an H on here, and you'd end up with a BH2 here, which through an oxidation process, we'd oxidize the borate up, and the bonds would migrate over from the B to the O. We'd end up with hydroxide here. This compound has an alcohol on an alkene, so we refer to it as an enol, and it can quickly, under either acidic or basic conditions, sorry about this, it can convert this H here. So if we deprotonate this H, this kicks in, those electrons go over here, and we pick another H up. So the enol readily turns into a carbonyl. So I want to emphasize that this H right here is this H right here. So it can move over, not directly, maybe isn't the same H, but this one gets deprotonated and deprotonate here, and the pi bond moves in between. So it's known as tautomerization, and we'll talk a lot about it in the carbonyl section, but for now, I want to mention that the enol turns to a carbonyl. Our carbonyl in this case is an aldehyde, can also be a ketone as necessary. Okay, problem with this reaction, comparing an alkene to an alkane. With an alkene, we had the group up here and group up here, so sterics was a little more pronounced. Here, the sterics isn't as pronounced because it's sp hybridization. It ends up the first BH3 could go on with a boron on the more substitute and H on less. And depending on temperature and other conditions, the percentages vary. But let's just, to toss a number out there, let's say 30% went with the boron here, 70 with the boron here. So we've lost efficiency in the first addition. But if you recall, it adds all three H's. So that's what it does one time, but the second time, it's going to have this massive R group attached. So it's going to have this alkene like this. So now the steric hindrance gets greater. So whereas the first time it might have been, let's say, 30, 70, next time it might be 1 in 99. And then when we go for the third one, it might be as high as, let's say, 0.01 and 99.99. So in the end, we're averaging out to get about 90% here, 10% here, which is still pretty good. But why waste these two steps when you can have something like this? And so what we actually use, let me erase everything. What we actually use is something called 9-BBN, where N is no name, meaning it's a large cyclic system. I'll draw it at the tail end. But it's a bicyclic compound. It's very large, and it has a boron in it. So instead of starting with just 3 H's, we now are going to start with an H connected to a B and a massive ring system. I'm going to redraw this because it's the bat. But it goes on, it's so crowded that it goes to the less hindered side over 99% of the time. So it selectively goes here because we do that. But note, here I need a 1-to-1 ratio. Here I need a 3-to-1 ratio. So when I do this reaction, I only need 1/3 an equivalent. Here I need a 1-to-1 equivalent. That's fine. Okay, so key thing, it forms an enol first, which undergoes tautomerization. That is the spelling of it. Tautomerization, again, is a process where we lose an H here. Those electrons swing in to form a double bond to the O. This double bond breaks. With those new electrons, it picks up an H over here. So again, this H here is actually located here. I'm going to do a thing on tautomers, but it's actually going to be its own video because tautomers belongs with carbonyls and alcohols, because you are, after all dealing with an alcohol going to a carbonyl. But it pops up here. We're introducing it here because it's part of this process. So you end up with an aldehyde. So when we undergo hydroboration of alkynes, instead of getting an alcohol, we end up with a carbonyl. Instead of 1 bond O, we end up with 2. The anti-Markovnikov version ends up with what's known as an aldehyde if you do it on a terminal. And then we'll look at the next one, and that is where we do it on a non-terminal. Note of interest, this is the compound I was talking about. So 9-borobicyclo-331, nonane. So here's my nonane, and here is my boron bridge. So that's kind of what I was trying to draw there. Nice crowded side here. So H is distinctly smaller than B with the giant R group. So it goes to the more hindered, boron goes to the less hindered. Okay, so what if we want to do it in instead of an anti-Markovnikov fashion, we want to do it in a Markovnikov fashion? So in this case, just like we did with an alkene, we added Hg. It was actually in a +1 state. We had a couple acetates on it. This time we're using Hg, but we're using it in a +2 state, because if you recall, sulfates carry a -2 charge. So mercury carries a 2+ charge to offset it. So we're dealing with that. Note here that this time we have a carbon here. It's an internal carbon that's getting the O, but it's the exact same story. We're going through an enol first. That enol turns back into a carbonyl. So in this case, it's an enol to a ketone. That's your tautomerization. The previous one was an enol to an aldehyde. Okay. If we use, instead of a terminal, let's say we use an internal alkyne, it ends up that we get both carbons. There is no preference. There is no Markovnikov versus anti-Markovnikov in this case, because they're equally substituted. So unlike an alkene, where we can have two R groups versus one, two H's versus none, that situation here, we have an R no H's, an R no H's, they're equal. So there's no preference for one side over the other. So we end up getting both. Now, the truth is it might be like 55-45, might not be exactly 50-50, but it's in the ballpark. Okay, onward we go. Note that this is a methyl ketone. We get absolutely no aldehyde in this case. So at least, whereas it's not necessarily selective when it's internal, highly selective when we use the alkene or the terminal alkyne to get the alkene where the O is going on the more substituted carbon. Okay. How does this happen? So mechanistically, we want to look at this because it's kind of a carryover from before. It's similar, but still want to look at it. Instead of Hg plus like before with the OAC on it, it's two charges. So highly electron receptive. It takes this pi electron from the triple bond and you form a carbocation. And the truth is, once I form this is sp, so it can be, this is linear. This is at this 120 angle because it's now sp2 at this carbon. And when the Hg comes in, when it does this, it's going to angle over a little bit. The H should come down and it should push the arc a little bit. I didn't emphasize it because I want to actually emphasize the opposite, where the Hg isn't symmetrically located in the middle of this triangle. Because the steric hindrance being less with an H than an R, it's going to stay slightly to the right, meaning this is treated as a full covalent bond. This is a partial or a coordinate bond. So the result is this carbon, the more substituted, still has a partial positive. This carbon is essentially neutral. It's important to make note of that because the next thing coming on is water. It has to make a decision. You have a lone pair, you can attack a neutral carbon or you can attack a positive carbon. And the water, as we know, negative nucleophile will always try to find positive. So the delta minus finds a delta positive. In doing so, it adds specifically at the more substituted carbon. Okay, so we have this. We now have a positive charge, so this is easy enough to deprotonate. Another water comes in, pulls off the proton, and we have essentially an enol, but with mercury still bound. Because the mercury coordination, it doesn't tautomerize quite yet. What does happen, though, is we now have an acidic proton, and we have an alkene, so the alkene can pick up the H. When it does, we now create a carbocation. So this is just like tautomerization in the sense that we protonate the alkene, and then the electrons can kick in, which they do. They come off of OH. So we now have this double bond to O, protonated, and an Hg. Rather than deprotonating and stopping at that point, so turning the enol into a ketone, it actually takes electrons from Hg. Hg is more willing to give them than the H. So Hg will put electrons up here and kick that density back up. And you end up, as I've drawn it, with an enol. We are definitely not done. We know enols are not the most stable. So this enol will eventually go to a ketone. So eventually you're going to get the R, double bond O, the H, and then I'll emphasize another H. And so actually, I really should put it, emphasizing that the water we added is an O on one carbon and two H's on the other. So eventually we will get to the ketone, but I just want to stop the mechanism at the enol. And that is what I think is the more interesting part of the whole thing. So hopefully you're looking at this and saying that's kind of the same thing that happened with the sodium or the BH3 when we did an alkene. It's a little different, the intermediate, and then this is the same, when we did the mercury acetate. So again, a little bit different because of the enol, but similar type of mechanism, same ideology going on. Okay, so this is the start of the reactions associated with alkynes. And again, notice they are very, very similar to alkene reactions. So much so that I keep on making the same error, saying alkene and alkyne. because there is not a lot of difference other than slight change in stereochondrites makes us exaggerate our reagents. Well, hopefully this went well, and I hope to see you at the next podcast, but we'll tie this one off. So have an absolutely wonderful day, and